If you've ever looked at a soccer ball, you might notice that there are 12 pentagons and 20 hexagons. Funny thing is, any polyhedron made of pentagons and hexagons must have exactly 12 pentagons, even in some kind of mutated soccer ball. And that's because of something called Euler's characteristic. It describes the structure of an object, usually represented by the Greek letter chi. For polyhedral surfaces, it's equal to the number of vertices minus the number of edges plus the number of faces. And this always equals 2 for all convex polyhedra. But how do we know it always works and there doesn't exist some weird exception lurking around? Well, imagine if you could expand the bottom face and collapse the 3D polyhedron into a 2D graph. The overall structure of the polyhedron doesn't change, except that the bottom face is now everything else. Now, add edges until each face is a triangle and start removing edges and vertices along the boundary. Notice how the faces disappear as well, so you end up with a process similar to how one could cut pieces of a cake. And just like how the cake stays a cake while cutting it, v minus e plus f doesn't change no matter how you're going about it. The magic of this method is that no matter what you start off with, or how you cut the pieces, you always end up with a triangle. Now you just count what you need, plug the numbers in, and you get that the Euler characteristic of the triangle is 2, meaning that the Euler characteristic of your original polyhedron must have been 2. This explains the mystery behind the soccer ball and its variations. If you let the number of pentagons be p, number of hexagons be h, and add the relevant calculations, and there we have p equals 12. Well, there are no restrictions on the number of hexagons. This means that a soccer ball can look as weird as possible as long as it has 12 pentagons. Now that's a neat little formula which covers most of the 3D things you usually see, but that doesn't include things with holes in it. The Euler characteristic is the same for shapes which are homomorphic, which in simple terms means that if you stretch or squeeze one object in some way, you can get the other. Any convex polyhedra is homomorphic to a sphere, including your soccer balls. But what about objects with holes? Well, we have chi equals to 2 minus 2g, where g represents the genus or number of holes in the object. A donut has chi equals 0, and fidget spinners have chi equal -4. So it turns out that almost any surface is an Euler characteristic, and you can calculate it using a similar method as the one before. Divide the surface into triangles, and then apply v minus e plus f. But that's only for 2D surfaces. What about 3D or even higher dimensional shapes? Think of a point in the nth dimension as needing n coordinates in order to define its position. Then the equivalent of a shape in the nth dimension can just be a set of points and their neighbours. If you look back on v minus e plus f, you'll notice that a vertex is just a point, which is 0-dimensional. Edges are 1-dimensional and faces are 2-dimensional. So if we let ki represent the number of cells of dimension I in the object, we can extend the pattern for higher dimensions. This number could be considered the origin of topology, the study of shape and space. It can be used in computer chip design, software networks, and even in the study of the shape of the universe, which shows just how a small thing can have a huge impact on the world. Thanks for watching.